Alright, we're going to look at a Newton 2-type problem. This problem is similar to a problem that's in the Shalm's Outline series for college physics, that is trig-based type physics, APB. But it's good for any type of course. It says a member of a grounds crew is using a roller with a radius of 30 centimeters. So 30 centimeters means that the distance between the center of this and this right here, that distance there, that happens to be 30 centimeters. It says that this thing has a height step right here that's 12 centimeters. I happen to know that this total distance is 30 centimeters, so that tells me something. It tells me that this distance right there must be 18 centimeters. And like I said, this right here is 12. So I've got a triangle here. $18 centimeters. I'm sorry. My fault. Back up a little bit. 30 centimeters. 18 centimeters. And if I look at that, 6 times 5 would give me 30. 6 times 3 would give me 18. You can use Pythagorean theorem. You can see that this is a 5, 4, 3 triangle. So 6 times 4 would be 24 centimeters. And this is some angle alpha that I don't know, which is right here. There's also an angle here, theta, on this handle. Let's see anything else on that. So I have that. I was told the mass was 10 kilograms. So I've already put the 12 centimeter high step in. It says, what is the minimum force on the handle? Okay, what is the force here? A person must apply to clear the step when the handle makes 30 of angles of 0 and 25 degrees. So we'll do the first one for 0. The minimum force is found when the acceleration of 0 meters per second squared. So it's an equilibrium type problem. So AX is equal to AY is 0 meters per second squared. And the ground supplies no normal force. So the ground, which is down here, when you are lifting it, is not any more pushing on this. Alright, so let's draw a free body diagram and see if what I have helps out a little bit. Oh, got this big diagram like that. Isolate the body. There is a force this way, F. It's at an angle of alpha, I'm sorry, theta. There is a force of weight pulling down. So remember, when you do a free body diagram, weight, applied, normal, tension, friction. So we're not dealing with the friction in this problem. It's not sliding or anything. Tension, no, there's no tension, there are no ropes. Weight, yes, I got the weight. Applied, yes, that's F. So that one I've taken care of. Normal. Well, there's not a normal on the bottom. It says that. But there is going to be a normal perpendicular to the point of contact from this step to that roller. So there's a force pushing it along this direction. So I'm going to draw that. And that angle is going to be this angle alpha. Now, let us write our equations for x and y. The sum of the forces in x has got to be 0 because it's equal to mass times acceleration, and I'm told that there is no acceleration in x. And the sum of the forces in y, they have to equal 0. Now along x, I have a part of the force of F lying along x, this side, which is the cosine. So I have f cosine theta, and that's in the positive direction. I have part of the normal force, this side, which is adjacent, so I need the cosine, and it's in the negative, minus n cosine alpha, and that's got to equal 0. None of the weight lies along x. So that's one equation to solve. Another equation is from the y. In the y, I have this part of the f, which is the opposite. So f sine theta, and that's going upward, so that's in the positive direction. I have this side of the normal sine of alpha, and that's also going in the positive y, so that's a plus. And then I have w, all of it, going in the negative. Minus w is 0. That's equation number 2. Now, I don't know the normal force, and to actually solve this problem, I don't need to know the normal force. So what I'm going to do is I'm going to isolate the normal force in both of these equations by themselves. So n cosine alpha is going to equal f cosine theta. And over in the second equation, n sine alpha is equal to w minus f sine theta. So that's just rewriting equation 2, and that's rewriting equation 1. I'm going to take equation 2 and divide it by equation 1. And what that's going to do is cancel the n. This is a standard thing when dealing with transcendental equations, as equations have trig functions, that if you have an unknown magnitude, you divide. If you want to get rid of the angles, because you didn't know the angles, then you'd square this equation, you get cosine squared plus sine squared, add them, cosine squared plus sine squared is 1, you get rid of the trig function. I want to think I can find the angle. I want to get rid of the n, which I don't know the normal force applied by the step. So if I do that, I get n sine alpha, and I divide on the left hand side by n cosine alpha, and over here I get w minus f sine theta, and on the bottom I get f cosine theta. This cancels, so I get tangent of alpha. I've got w over f cosine theta, and on the second term the f's cancel, and sine over cosine is tan of theta. So let's put these guys together. Tan alpha plus tan theta is equal to w over f cosine theta. I'm going to bring f cosine theta over here. I'm just going to bring the f, I should say, not f cosine. And I'm going to get, for w, mg. And on the bottom, I'm going to have tan alpha plus tan theta times cosine of theta. And that would be good enough to work the problem. But you might want to simplify it as follows. F is mg tan alpha cosine theta plus tan theta is sine over cosine. The cosine will kill, and that just leaves sin theta. Either one, this equation or this equation, is good enough to work the problem. This is basically the equation for the force for any angle, and I was specifically asked for 2 cases. In part A, I was to solve it for theta equals 0 degrees. So F would be equal to mg over the tan of alpha. Now I need to know the tan of alpha. Now it turns out tan of alpha is known. Let me go back and look at that for a second. Tan of alpha can be found from this triangle here. It's 18 over 24. So 18 over 24, that's 3/4. So the tan of alpha is 3/4. And it's set for all problems here. So going back to my equation, I have mg 3/4. Then I have the cosine of 0, but the cosine of 0 is 1. Plus the sine of 0, which is 0. So you have to lift 4/3 the weight of this particular roller. Now let's see, looking back at my notes here, what the particular mass was for this roller, and see if I have that here. You can look up directly up on yours, but I actually have to sort through mine a little bit. Let's see, the mass was 10 kilograms. So 4/3 times 10 kilograms times 9.8 meters per second squared. So punching that into a calculator, gives me 131 newtons. Now, notice that if you pull at 0 degrees, it's worse. Not only you have to lift all the weight, but as you smack into this ledge, you got to be able to pull it up. So you got to be able to pull it over that ledge, and that's why the force goes up. Let's look at B. At B, we were asked to do it for a different angle. It says 25 degrees. So F will be equal to, we have 10 kilograms, 9.8 meters per second squared. And then on the bottom we have 3/4 times the cosine, going back up here, times the cosine of my angle. So the cosine of 25 degrees plus the sine of 25 degrees. And we put that into our force. And I come with 88.9 newtons. Whoops. So it takes less force. This isn't surprising. Anybody's ever tried to pull a buggy over a step or anything else knows that you lift up on the buggy to get it over the step. And we just proved that the laws of physics say that's exactly what you should do. All right, that finishes this problem.